Question 3 asks us to estimate the area under the curve f of x equals 1 over x squared between x equals 1 and x equals 4 using the right endpoints and 5 rectangles of equal width. Use the graph of f to explain whether your estimate is an overestimate or an underestimate. So the first thing we want to do is we need to calculate the width. We weren't given it in this problem. So we know that delta x is b minus a over n. Our b is 4, our a is 1, and we were told to use 5 rectangles, so each rectangle is going to have a width of 3/5. So that can make things kind of tricky when you have a fraction we got to keep adding to these whole numbers. So one thing that can really help before we write our subintervals is let's re-index the scale so that the denominator is in terms of 5. So 1 is the same thing as 5 over 5. 2 is 10 over 5, 3 is 15 over 5, and 4, is 20 over 5. So now if I'm writing my subintervals, well, it starts at 1, which is the same thing as saying 5 over 5, and I add 3/5 to that. So 5 plus 3 is 8. Then I pick up the next rectangle at 8 over 5, and I add 3 more, and I end up at 11/5. The third rectangle starts at 11/5. I add 3 more, and I get 14/5. Then we start at 14/5, go to 17/5, and then the fifth and final rectangle will start at 17/5 and end up at 25th. So we do in fact start from 1 and we do end up at 4. Now when I sketch these rectangles using right endpoints, I can see that scaling everything to 5 helps make this a little easier. So 8/5 is probably, we'll say, about here. 11/5 is going to be pretty close to 10. Then we're going to go to 14, that's going to be just before 15. 17 is going to be about somewhere kind of in the middle here. And then we'll end at 20. So if we're using right endpoints, then I go to the right edge of my first interval. That is the height of the rectangle, and I connect it back. And I'll follow that all the way across. So before I even calculate the area and get a value, I can already see from the picture that the area we get is going to be an underestimate because we have some gaps between the rectangles and the function itself. So when a function is decreasing like this, the right endpoints are always going to be under the function. If this function were decreasing and we used left endpoints, we could see the rectangles would extend over. So sometimes when you look at solutions, you might see the increasing, decreasing kind of correlating with the endpoint rule, and I find it easier to just do a rough sketch and see what it looks like. So now we need to know what our heights are. So our heights, because we're using right endpoints, our values of each kth rectangle are the right endpoints. So 8/5, 11/5, 14/5, 17/5, and 4 are what gets plugged into our function. So the area is going to be approximately equal to the sum from 1 to 5 of f of ck times delta x. So what the k allows us to do is it allows us to adjust the number we're plugging in to match which rectangle that we're dealing with. Since delta x is the same, I'm going to factor the 3/5 out front, and then I'm just going to sum up the heights because we know we're going to have a 3/5 attached to every single number. So another thing we can do here to make our lives a little simpler is notice the function itself. The function is 1 over x squared. So if it were x squared and I plugged 8 over 5 in, I'd get 64 over 25. But since it's 1 over x squared, I flip the fraction upside down. So we can actually do this fairly quickly. So 8/5 squared is 64 over 25, but if we flip it, right, it's 25 over 64. That means 11/5 is 25 over 121. 14/5 is 25. I would just write 14 squared because I don't have that memorized. 17/5, 25 over 17 squared, plus 4 squared is 16, so 1 over that is 1/16. And you can just leave it like this. I don't think there's any reason to go any further. And we know from our picture that this is an underestimate. The rectangles do not capture all of the desired area. So we can see here, this is why like a traditional equal sign would be inappropriate here. It's okay to put this equal sign here because I'm saying this is what the summation equals, but the area is approximate to that because we can see all these gaps that we've not accounted for in this method.